Okay, everyone, let's start. In the very beginning of the class, I just want to mention again that we have where it is homework number one. You will have two homework assignments in this class plus final exam. So, uh, it will be. I forgot the distribution. You will need to check it via the syllabus. Let me see here. 70% homework, final exam gonna be 30%. So it's pretty important. And I believe the homework is due on Thursday, if I remember. Yeah, June 12th, Thursday. So 2 more days. Please, start ASAP. Do not delay till the last day because there could be many uncertainties, including the CPU usage time or something, or in case you have any installation problem or something. So start ASAP. Okay. So now today we're gonna introduce uh k-nearest neighbor KNN. So let me direct it over here. So KNN is a type of classification. So I guess I'd better start with introducing classification first. I believe in the very first lecture was mentioned. I'd better give me a second, take it out. Lecture one. Where's my lecture one? Okay. So we have a like a big picture, which is let me see here, which is supervised. Let me take my annotation, which is the supervised learning and unsupervised learning. So supervised learning, two most, I would say, typical problems for supervised learning are the classification and the regression. And we've already finished a basic introduction to regression problems. And now we're going to go to the classification problems. And so these two are the supervised learning. After it, we will mention a little bit about unsupervised learning. So here, classification is one of the supervised learning. It's actually, to be honest, probably the most important element in supervised learning. One, I should say one of, because regression is also very important, and the pattern recognition. So basically, each observed data point includes a response variable, which is the label that indicates the class or class label or category. Those terms are equivalent to which the data belongs. And the number of classes is known in advance. The goal is to predict the class of a new unseen data. So, for example, here in lecture one, we mentioned something like a dog versus cats. Remember it? Here we're going to mention again, for example, suppose we have 1,000 pictures of cats, 800 pictures of dogs, and each image, let's say it's 200 by 200 pixels. So each picture, you will get in each picture, you will get a label. For example, this is a cat. This picture, suppose it's 200 by 200. This is a cat label. And this picture, it's a label, is dog. For example, this is the third picture, the label is cat. The fourth picture, the label is cat, something like that. So now we have 1,000 such cat pictures for cats. For cats means the label of these pictures are cats. And 800 pictures of dogs, meaning that all of these pictures, the label is dog. Okay, each picture is 200 by 200 pixels and, labeled cat or dog. Okay, now I will get, for each picture, I will get a vector of length 40,000. Why? Because see, I have 200 by 200 pixels. I can just simply make each pixel, as a color or something, and then 200 by 200, 40,000. Hence, I have, I just, instead of a matrix, I read it as a vector. So now I have 1,000 plus 800 pictures for training. Each picture is a vector of 40 with 40,000 elements. And the total number of classes is m equals to 2, which are cat or dog. Okay, now I will give you a new 200 by 200 pixel image. And then I'm going to ask you, hey, whether it's a cat or a dog based on these 1,800 training pictures or training vectors. So that is a very typical classification problem. And the setup of classification here is very similar to regression. Uh, here we're going to build a function actually y equals to fx, where this x is the observed data. Where to keep my notations consistent, here I use p-dimensional as well, meaning that I have p features. So for example, here the p equal to 40,000, meaning that I have 40,000 pictures. Each is a pixel of the image. And then I will have a scalar y representing the label. For example, y equals to -1, indicating cat. Y equals to +1, indicate a dog. So now each observed data with its label forms a pair, which is x and y. Be careful here. X is a vector, and hence you can see it's in bold. It's a vector. For example, x can be a vector including 40,000 elements, and y is a scalar, meaning the class. For example, -1 cat, +1 dog. So if f is linear, then it defines a linear classifier. Recall that in linear regression, and go to which class? Let's say lecture 3. We did something similar. Remember here? We also wrote it, let's say the vector form, where it is. We also wrote it to be, where it is. We also wrote it to be something like here, see here, fx equal to this. The difference is that because here it's a linear regression. So by definition, linear regression means it's a linear function. And then we also write like, we're writing this way. We have a semicolon, beta vector, beta 0. This is just to, it's a notation just to let you know that the beta and the beta vector and the beta 0 scalar are parameters. It's actually similar things here. But here, because we didn't mention which specific classification methods, so we just write it as fx without like fx column beta. Later, you will actually see it's basically the same. So using this system, we can build something very, very similar, to regression mathematically. Okay, now, excuse me. Here, a key difference between regression and the classification, what we're mentioning here, is that in classification, the domain of Y is typically a discrete set of integers. For example, suppose there are n classes, so we can simply set it to be, so C is the set for the label space. I can set, for example, C equal to 1, 2, 3, 4, 5 till m. Why? Because we totally have m many classes. Or we can write it like Python. It uses 0 as the first index. So we can say 0, 1, blah, 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 till n-1. The same, as long as the total number of elements included in this set, it's n, then done, that's it. Specifically for binary classification problem where m equals to 2, it's convenient for us to make it to be -1, +1. People may ask, so why don't you make it to be 1, 2 or 0, 1? Yes, you can. However, later, especially when we mention support vector machines, SVM, you will see that it has a mathematical advantage if we define it to be -1, +1. It's just a pretty magic mathematical models. You will see it. Okay, so there are actually many classification methods available. In this course, again, it's a pretty short class. I mean, I worked very hard to make it works in 6 weeks. We're gonna only cover some very fundamental but important, powerful ones. There are k nearest neighbors, which is KNN, which will be introduced in today's lecture. Naive Bayes, I'm not sure when I can cover naive Bayes today, but for sure next week, next class on Thursday, we will cover it, logistic regression and support vector machine. And this class, of course, is on KNN. Okay, so let me first give you an intuitive example of KNN. You will understand what it is. It's actually super intuitive, super simple, but very powerful. So consider those observed data. To make my life easier, I just use different color. Those blue and circle blue and the diamond red colors. These I'd better give me 1 second. Let me just use pen. Those and those are sorry. When I say those, please ignore. Delete this one. Okay. Those blue and the red points are my training data. And remember, we said, okay, it's a classification problem. So for each training data point, you should have a label class label, right? Okay, so I just use color. When you see a circle blue, that means the training data belongs to class one. When you see the diamond red, that means the training data belong to class two. So, okay, so these are my training data. Now I'm gonna give you these two triangle, the green triangle points as target data points. So I'm going to ask you, hey, look, I have two target data points here. Based on these so many, I don't know how many training data, tell me which class should this target data point belongs to. How about target data point two? Intuitively, I guess everyone gonna say, hey, simple. See here, target data one is surrounded by so many blue points. So I'm gonna say they should belong to what belongs to the blue data class one because those blue training points are class one points, right? Similar things for this target data number two. It's so close or it's around those red diamond points, and since red diamond points are class two, so I should classify target data number two to be class two. You're absolutely correct. And this is exactly the meaning of KNN, which is K nearest neighbor. Okay, formally, we're going to say, given a hyperparameter K, still remember hyperparameter, what did we use to determine the hyperparameter? Remember the cross-validation method introduced in lecture 5. Okay, so suppose here it's already given a hyperparameter K and a target data point X. Again, X is a vector with an unknown label. And the KNN algorithm classifies X based on the majority class label among its K nearest neighbors from the training data. What does it mean? So first of all, since X is a training, so sorry, since X is a target data, of course you don't know the label because that's my question. I'm gonna ask you from, hey, look here, we have three classes, those blue ones are class one, what are these? Orange heart are class three, red diamond are class two. So this is target data. I'm gonna ask you, hey, what is the label of this target data point? That's my question. So you want to know the label of this unknown of this target data X, right? Okay. What KNN algorithm does is to classify it to the majority class label among its K nearest neighbors from the training data. So let's just take this as example. Suppose K equals to 1. K equals to 1 means what? K equal to 1 means the one nearest neighbor, or you can just, just the nearest neighbor, right? Okay, so you look at here, which one is the nearest among all those, those three classes of the data training data points? Which one is the nearest? Clearly, it's this data, right? Let me just give me a second. Let me just plot it. Oops. Let me use. So clearly, this point, why it's so thin. Well, a minute. Let me see how can I make it bigger. Okay, hope it's bigger enough. Yeah, big enough. Clearly, this point is the nearest point. Okay, so what is the class of this point? Class one, right? Okay, see, I will determine this target data by the class of the nearest training data. And hence, if k equals to 1, I'm going to claim that the target data belongs to class 1, right? Okay, now let's see, what if k equals to 6? K equal to 6 means what? It means I'm going to looking for the 6 nearest neighbor among all my training data to my target data. So look at the 6 nearest neighbors. What are these? Again, sorry. Okay, make it bigger. Okay, so 1, 2 are here. 3 is here. 4, 5, 6. Sorry, my hand is a little shaky. I just actually ran from the gym today. a bit hurry. Sorry about that. My hand is shaking. Anyway, hope it won't impact, have a negative impact when I'm coding. I'm just like dancing on a keyboard. Okay. So when my k equals to 6, you're going to see here, I have 6. These are the 6 nearest data point, training data points from my target data, right? Okay. And then see what is the majority. We can see that among these 6 data points, one of them is from class 3, 2 of them is from class 1, and 3 of them are from class 2. So what is the majority? Clearly 3 of them, right? And hence, if k equal to 6, I'm going to classify this training data to what? To this one, to this red group, which is class, class number 2, right? Okay. Finally, very similar things. What if I say, hey, my k now equals to 10? So what I'm going to do is I'm going to find the 10 nearest neighbor, which are 2 are blue, 3 are red, and 5 here, my hand is still shaking, sorry. 5 are orange. And what is the majority? Clearly 5, orange is a majority. And hence, I'm going to classify it to the orange class, which is class 3. So these are, demonstrated here. And now you understand the point of k nearest neighbor. Super, super simple, which is for a given k, I just need to find, among all the training data, I just need to find its k nearest, neighbors among the training data. And then I'm going to choose the class of the target data X to the majority label class among these k nearest neighbors, which are, which is demonstrated here. So that's the thing. It's super simple. One thing I do want to mention is the assumption of the KNN. It is based on the assumption that similar objects tend to be located close to each other in the feature space. In other words, the nearby points are likely to share the same class. I would say in the real, those kind of real world problems, such assumption is, in most cases is correct. Of course, it depends on how you define the feature classes. Here, what I'm talking about is just based on our human like human intuitive. I would say, in most cases, you can try to select a feature space to make this assumption correct. Uh, Clearly, KNN is very, very simple. It's a very, very, simple algorithm. However, later you will see in many cases, KNN is super, super powerful and effective. And also KNN, later, I'm not sure how many of you are familiar with the computational complexity. KNN, the computational complexity is super high. However, it also suffers something which is, for example, like the selection of k, which is going to be like a bias variance trade-off. Anyway, all those we'll mention later in this class. Okay, so after introducing this this super super simple after introducing this super super simple uh, example, let me first show you how to code it, make it, in Python. I will need this data, so sorry, I will need to cheat it because otherwise I cannot remember that those parameters. So I'm gonna go to Jupyter Notebook, and then I'm gonna this what is it, lecture 6? Yeah, this is lecture 6. Sorry. Okay. I will create a lecture 6, first show the numbers, and let me make it bigger just in case you cannot see it. Okay, so what I'm gonna do is first I'm gonna import NumPy std, import matplotlib.pyplot.splt. Here, still we'll use scikit-learn, but we'll from scikit-learn.neighbors, since we're doing k nearest neighbors and neighbor, import k neighbor classifier, Okay, so first of all, I will generate the training data for 3 classes. So currently, to be honest, I'm copying and paste because I cannot remember the parameters. So this n means, I'm gonna use this to store the number of samples in each class. So I'm gonna have an x1. Here I just want to randomly generate the training data for the three classes. I'm gonna use np.random dot multivariate normal. So it will randomly generate data from a distribution called a multivariate normal distribution. I believe we'll mention it. Yes, we'll mention it later in what in logistic regression and possibly SVM a little bit how to generate those things as well. But it's just like a normal distribution. But here's not multi-normal, meaning that from here I make it to be 2D, which means it has just consider like it has two directions, x and y. Both directions are normal distributions, so that these are the mean, let's say mu x and mu y, and then I will have a covariance matrix sigma. The parameters are 25, 6, 6, 36. Again, here I'm just, I'm reading it actually because I have a double screen. I'm cheating here. So this line means I'm gonna use, I'm gonna generate 50 n equals to 50 random data points following the multi-normal distribution in which the mu x equal to 10, mu y equal to 10. And this one is a covariance matrix. This is sigma xx, sigma xy, sigma yx, sigma yy. So again, for the details, mathematics something. If you're interested, I'll introduce it later. Here, just to let you know, it's generated. It's generating such data. Y equal to np dot one n. So this will generate just n is 51. So for example, I can just y1, and you will see it. So you can see it's all. Of course, I can do x1, but I mean that's just very difficult to be determined. So each number will be the xy coordinate. So for example, in this point, that means x equal to this, y equal to this, and so I have those 50 points. So later I will plot it, so I can visualize those points. So this is the meaning. Okay, so this is for class one. For class two, I'm gonna do the similar things. Random dot multi. Oh my God, I can feel my fingers are shaking. But anyway, sorry. Multivariate. Okay, now I have. Let me see what is the parameter. Negative 10, 10. And then the covariance are 28, and then 8, 25, here's 50, y2 equal to mp dot 1's n. However, be careful, since I have three classes, I want y2 to be this way. So in this case, if my y2 going to be 2, you see what I mean? So that later I will print x1, y1, so that it can show me that okay, that 50 points, the label is 1. Here for x2, these 50 points, the label is 2. And the similar things I can do this for x3. So that 3y3, here the 3 times here, and then I just change those parameters, 0, negative 12, and here is 20, 1, 1, 49. Okay, so I have these, I've generated all those points so that now I can just plot the generated training data now. So now it's very easy, plt.plot and x1, 0. Later you'll see we'll concatenate, which means to combine all these data together. X1, 1, red dot label equal to training data class 1. And I'm gonna just copy and paste data for class 2 and class 3. Okay, so here we have done this, and I mean we can just plot it first, and then plt.show. I can just temporarily have a look at this. So these are my generated data, my generated data for training data. Of course, every time you rerun it, it will be different, of course, because it's randomly generated. Okay, so now I'm gonna do the KNN classification. Also, sorry, classification. Okay, so what I'm gonna do first, because x1, x2, x3 are my training data. Y1, y2, y3 are my training the labels for my training data. However, remember when we fit it, we write it like this way, right? Model dot fit x1. Of course, I know I haven't returned model yet. I know it, but we want to make one matrix here. But my training matrices are x1, 2, 3, and the training labels are y1, 2, 3. So what should I do? What I can do here? I can use x equal to np dot concatenate. Come on, I don't come here. Okay, no, I can spell it because typically, I mean, once you run it, you press table, it will show automatically concat in case you misspell it. Like people, like me, I always misspell. I'm not looking for any excuse because because I just finished the gym, my hands are shaking. No, I'm not even looking for it. The truth is, it's too easy for me to misspell something, so I always press table. Okay, so here x1, x2, x3. So this means I'm going to concatenate x1, 2, 3. Here, one very important thing is x is equal to 0. So the meaning is this. So suppose, let me just plot something. Okay, so suppose this is your x1, this is your x2, this is your x3. It doesn't matter the length as long as the widths are the same. So if I say x is equal to 0, that means I'm going to concatenate it this way. You see what I mean? In other words, it will be concatenated by rows. So this will be the whole x1, x2, and x3. This is how I concatenate it. However, if I write it to be x is equal to 1, then it's going to be different. X equal to 1, that means it will be concatenated in this way. It will be, for example, x1, x2, x3. It will be concatenated by the columns. So be very careful, okay, when you are using x equal to np dot concatenate, be very careful what is the axis here. So in this specific case, actually, as long as like in machine learning for training, by default, we have those kind of rows means different data point training data points, columns means different features, and hence in this under this assumption you always want to concatenate by rows. Why? Because you have different like x1, x2, x3. You want to make all these to be training data while keep the same number of columns. Let's say here I have two columns which are like x, y, z, x and y, right? Hence, you should choose x is equal to 0, but Python concatenate them by columns. Okay, so sorry, concatenate them by rows. Here, np.concatenate y1, y2, y3, and similar things, x is equal to 0, and hence now I have x and y. So if you don't believe, simple, let me actually call. I can just, I can just, let me use another cell. And then I can, for example, print y. And then you can see it's all 51s, 52s, and 53s. And I can just, for example, I can just print y dot shape, and then you will see it. Y50 by 1. See, Y150, because each y, y1, y2, y3 is 50. So that's the thing. Okay, so now let me just remove it. Okay, so now I have x and y. What I'm going to do is I will train the model. So model equal to k neighbor classifier. Here we do need to have a hyperparameter, which is k. And here you can see I have a key parameter, which is n neighbors. So if you don't say anything by default, it will set n neighbors to be 5. But here, let's suppose I wanna change it. Let's say suppose I have n neighbor equal to 5. Let me see. Yeah, in my example, I use a 5. And then here now I can do model dot fit xy. And then I can do the test data. Here I'm still cheating. I'm using test data equal to np dot array. So np dot array means I'm gonna generate an array, and then I'm gonna have 15, 15 as the first data point, negative 15, 10 as the second data point, and the 0, negative 20. Uh, uh, you may ask, so why am I cheating? Why don't I just random make three numbers? And to be honest with you, the reason because I try to, I need to have a look where those three classes are, and I try to make each point belong to one class. That's why, when I was preparing the class, I actually tried many different data. So data forecasting, data point, and the training those parameter settings. That's why I want to make sure they are correct, because I don't want to, for example, like 3 points are all in the same class. It will be, pretty kind of like weird, if I can make a 3 points in three different classes, it's gonna be the best. So and y predict model dot predict and then x test, so that I'm gonna, let y predict to be the labels of the test of these three training, sorry, three test data points. And now I can simply just, plot it. So I can here, let's say I'm gonna plot the class of the predicted data. So I can have PLT dot, oh, wait a minute, wait a minute. Let me see here what I want to do. Okay, okay. Here, one thing is that because the point could be from from different classes. So here, let me put it back. I'd rather just, so here what I do is that I give it a different color, and hence I use a for loop, to make an if statement. The basic meaning is that if it's a red, the target data or the test data is red, it belongs to class one, then I'm gonna make it to be red. Otherwise, it's gonna be if it's class two, then it's gonna be green. Otherwise, it's gonna be blue. So let's make it for I in range of x test shape 0. That means, hey, how many test data I have here? Of course, I have three, but this is just makes your code more robust instead of saying in range of three. If y predict I equal to 1, meaning that if this is in the first class, then color maker equal to R triangle, and the label equals to test data class 1. Of course, I mean, traditionally, you can write it this way. Here, I just want to save my space. So, in my slides, I write it this way. It really doesn't matter. And then I'm going to have else if what y predict I equals 2, then color maker equal to G triangle, a label equal to test data class 2, and else color maker equal to B. Here I'm just using RGB, label equal to test data class 3. Okay, so finally I just make the plot. I will have PLT dot plot x test I0, x test I1, and then color maker. And then here I have a marker size equals to 10, and then label equal to label. Here we go. So clearly you can see this one is test data class 2, and those green points are class 2. This data test data class 1, and this data test data class 3, and and this just perfectly shows the KNN. Okay, this is of course you can just run different things, and you can see they're always the same, the result. Okay, so let me move move my slides here, and this is the result. Um, in the future lecture, it's actually probably the last lecture. We're gonna mention something about k-means clustering. So here, k nearest neighbor, it is a supervised learning, and hence, so for example, all those training data points, I'm gonna still give you the color, meaning that I'm gonna still give you the class label. However, for k-means clustering algorithm, I will not even give you the labels. It will be unsupervised learning. You will automatically use some algorithms called k-means algorithms to find the groups, or let's say pattern recognition. And then after the do something like the classification. It will be even more like more interesting, more amazing, but of course more difficult as well. We will see it. Okay, so sometimes we want to plot the decision boundary to make our classification easier. Why? Because here, for example, for any given test data, I can say, okay, it is, for example, like it is green here, it is blue here, it is red here. But what if I want to know a boundary? So after plotting the boundary, I can have a very, very clear view on the whole space, like where it should belong to class one, class two, and class three. It's gonna be more intuitive and more clear, right? So this is the meaning of decision boundary. So formally, it is the dividing line or surface that separates different classes in the feature space. So for example, here, we can clearly see all this region, the light blue region, it is class three. All this, green region, class one, class two, sorry, and all this red region in class one. So that's the thing. Basic idea of the point example, which is, remember, we use np.mesh grid to generate the X1 mesh, right? So we can use this one, do something similar, and for each point, we can just color it. However, if you just brutally write a for loop and color it, you can try, but I can tell you that the result is pretty ugly. And hence here, first of all, there are actually various ways to plot, but here I will use plt.pcolorMesh to make it. It's one of the easiest way you can do. You don't have to generate some many very like complex things. You can use this one directly and automatically generate the mesh grid, the decision mesh grid for decision boundary. Let's see how we can do it here. So where are the points the same here? Okay, they're the same. So then I guess I can simply just copy and paste. So let's do it here. Let me just copy and paste here to make my life easier. So first of all, I will generate those data, and yeah, I'm going to generate, and then I'm gonna plot the generated data, right? And then let me see. What I'm gonna do is give me 1 second. Classification. So here I don't need to I don't need to make it anymore since I mean here I'm gonna plot for the whole XY. It's instead the whole plane instead of a specific XY. So what I'm gonna do here is, so let me see here. I'm gonna, yeah, here I need to rewrite the codes here. So here what I'm gonna do is I need to generate a decision region. And then let me see here. I need to generate a spec. Let me see how. Yeah, okay. I need to generate a linear space here, and then use a mesh grid to have those points span over the whole plane. Here I use -10 plus 10 is just to make it a bit bigger. You see what I mean? Otherwise it will be something like this. It will be something like very very tight. It will be something like that. I want to make it like bigger, and hence in my code, I write it to be minimum -10 and a maximum +10, so that you can see the whole frame of the plot is like here. It is, it's just kind of like bigger. Let me just write it. It's just something like this distance I make it to be 10, and this distance to be 10. This is the meaning. Okay, but anyway, let me just code it. Oops, sorry. How to delete everything? Okay, delete everything. Okay, now let me code. Okay, now here to make this one, I will generate the space, the mesh grid, so that I will need empty the link space. Come on. Okay, now I'm gonna have x dot min -10, and then x 0 dot max +10. And then how many points? 100 points, I guess. I did 100 points, yes. 100 point. And then XX2 gonna be the same. But this is for Y. I mean Y-axis, that's for X-axis, and now I'm gonna use X1, X2 equal to MP dot mesh grid X1, X2. Okay, now excuse me, I'm gonna predict the Y, right? So I'm gonna have Y predict equal to model dot predict. Okay, be very, very careful here that when we make, when we use scikit-learn and we use model.predict here, your input must be row arrays to make it more clear. It must be a kind of a row array. And hence, I cannot write like this way. If I make it, sorry, if I make it like this one, I bet you it will be error. Let me run it and I'll show you error. So the error here, K never takes two position argument, but three were given. Why? Because if you, let me just, if you print x1, x2 is just gonna be the same. See it? It is something, or at a better dot shape. It's 100 by 100. It's not a vector at all. And hence you have to make it the input inside to be, this one to be a vector. So how to make it to be a vector? And we want to squeeze it. So what we're gonna do is first of all use np.array to make it. np.array gonna be a column vector, so I will make it to be .t. T means transpose. And then the inside, what I'm gonna do is this. xx1 dot ravel. Ravel means to make it to be a flat, flat thing. Dot t. So let me show you an example. Let's say let's say xxx, let's say 3x equal to, let's say 1, 2, 3, 4. So now I'm gonna print xx dot ravel. Do you wait, np dot array. See what does it mean? So before 1, 2, 3, 4 is like 2 by 2 matrix, right? Ravel make it a flat. 1, 2 become flat, 3, 4 together. So this is what Ravel did. So similar things here. I want to make XX to be Ravel. So here I have, I can print XX. The shape is 100 by 100, right? And we can do this. Let me first of all print X, what's the name? A shape and then X1 dot ravel dot shape. And you see the point, xx1 itself is 100 by 100, which is square matrix. But here I use the ravel dot the shape, and it becomes what? Becomes only one, becomes a row matrix. So that's the thing. And then I transpose it to the column matrix. And so now I should have the y predict. After getting this y predict, I'm gonna have a directed plot. So I can have plt dot plot, and then I can have x1, x2, y predict. Okay, be careful here. It's something like you convert it to this way, but you need to convert it back because so sorry, not plt dot plot. It's gonna p color mesh, plt dot p color mesh. You will convert the y predictor back, and I will use the reshape to x1 dot shape. So what happens here is because we are here using scikit-learn library to use model.predict. So scikit-learn library requires the input here to be a row vector, a vector. However, for p color mesh, it requires it to be a matrix. So here it's already a vector. So we need to reshape it to what? To the shape of xx1. So that xx1, xx2, and the y, it will be kind of like correspondingly the same thing. And actually you will see these xx1, xx2 are the xy coordinates, in this plot, while this means the color. It's somewhat like a color, actually. Okay, so now I'm gonna have wait a minute. First of all, we can already run it. Let's run it. Oh, great. NumPy has no attribute. Sorry, wrong spelling again. Okay, here we go. The problem is that I personally don't like this color, so I can actually choose the color. To this end, I need to load one more library. Where it's right here. I need to have format plot lab.colors import color listed color map, and then hence I can define the boundary color so that it will have the color that I defined. So let's do it here. So let me just here from matplotlib colors import listed. Come on, come on, come on, come on. Okay, here we go. Listed color map. So here I can define something like, for example, boundary color equals to listed color map. So here I can define my color. Uh, I will use light coral. Let me see here. Light coral, light green, and sky blue. I believe it will be throughout the whole class. Makes it easier because you know, Python itself always, I mean, I should say Matplotlib library always give you those kind of colors. Like the contrast is too high. I feel like my eyes feel not comfortable, and hence I will use this. And then here you can just have the C map equal to boundary color. And then here we go. So this is the result. And indeed, you can see I have the boundary, the regions for the what decision region as this. Of course, you can, create more points, make it a bit dense, like higher resolution. You see what I mean? It shows you a higher resolution. So yeah, that's how we make it. Here I use listed color map for a complete list of the colors. You can just see here, it is some documentations. Honestly, Matplotlib, their documentations are really good. It's not like nowadays many API documentations. Uh, I hate to complain, but some people really did a very, very bad job. I mean, the documentation is so bad. I mean, unless you're really, really familiar with those kind of things, otherwise it will be very difficult for you to learn. But Matplotlib, their documentation is really, really good. Okay, so this is how we can plot the decision region here. And I believe the next one, let me see here. Yes, it's the decision region. And the interesting thing is, you may ask, so here in my code, K is what I forgot. K is a 5, maybe. So what if I make a K equal to 3? I can change. And of course, let me make it smaller so that it can be faster. I don't want to take too much time. So K equal to 3, or what if, let's say, K equal to 1, which is the nearest neighbor, and I want to make a comparison. And indeed, later here you will see it does matter for different case. It is actually something like a like trade-off. It will be something like with a smaller K, you will have overfitting risk, lower bias. Otherwise, it will be, the reverse. It's actually really like a trade-off between bias and variance. But here, let's try to make a subplot here so that I can, directly plot those, let's say, four different choices, selections of K simultaneously. Okay, so let's just write a code here. And one thing I do want to mention that here, since we're in Anaconda Jupyter server, I mean a cloud server to run it, and hence it's not that convenient because I need to use IPY MPL. Remember what we introduced? What installed this package? Why? Because just to make it like a GUI interference so that we can kind of drag it. Uh, However, if you run Jupyter Notebook, let's say in your suppose let's say you install this one, the Anaconda locally, I mean this navigator, then you can simply just directly make it a Qt, and then you can just plot it. Here, but why I make it on the server? Because it's just easier. I mean, you don't have to install anything on your local laptop or the computer. As long as you have internet access, you can just do it. You know what I mean? Like everything's by server. So that's the point. However, again, if you want to run a real big project, I would recommend try to install it locally because I don't know how many hours it can take. If you may need to code for 10 hours, 5 hours a day, something like that. It could take you a lot of time. Of course, you can download GT, which is for like a GitHub, so that you can work together with anybody in the world as long as he or she can use GitHub, so that you can work together for some program for some projects. But anyway, it's a bit too far. That's another story. So let's see how can we plot it like K and decision boundaries for different values of K. So first of all, let me see. Do I need to cheat? Okay. Let me cheat it. Let me cheat it because otherwise I just worry I will make something wrong again here. Oops. Copy and paste here first. And then I'm gonna have what I'm gonna have the magic commander command matplot lib and ipy.mpl so that I will have the graphic things just in case. Let me just try it. Okay, here we go. So that's the difference. You see it? I have to control this. I can just move it, as whatever I want, and I can even amplify specific areas bigger, and then I can recover it. So it's a kind of a GUI interface. I can play with that. Okay, so now I need to change my code. Very first thing I need to cheat for the parameters and oh look wait look they're the same. Okay, no problem. Then we can generate code. We no longer need the cheating things. Very first thing is because I will use a for to what to write a subplot. I'm gonna remember how do we create a subplot, which is x equal to figure dot add subplot, and then since I will plot 2 by 2, it will be 2 2, right? Let me just write something here. Let me just write something. Oh, sorry. Later, I'll have something like this way. So I'll have x equal to figure, and then dot add subplot 2 2, something like this. For example, 2 2 1, 2 2 2, 2 2 4, right? And hence, I need to change the orders of many of them. So first of all, here's data generation. Yes, I can just make it. And then I will need to, anything related with the data, I need to handle this. Say, for example, here, I can make it outside of the for loop. And then I can, for example, let me see here, I can make this one generate this one as well, so that here's all those kind of XY coordinates. And then I can let me see, what can I do here? I can have I can have this one out. The decision boundary is going to be out as well, so that all those constants I should have. So now I will kind of like do the what here's generating the data for the three classes, and let's say get the constant lists and the variables. Okay, so now I will have plot the training data. So I can have, let me see here. It is here. Okay, so now I have the KNA classification. So here I do need what? I need a K list. K list equals to 1 3 5 20. 1 3 3 5 20. Okay, so then I'm gonna run the for, right? So first of all, I need to create a figure equal to plt dot figure. So this is to let Python know that, hey, I'm gonna really create a figure here. Now I'm gonna write a for loop for I. Be careful here. Since each plot, remember, where it's gonna be here. So here I will use an index called I, and hence the I would say I is in like the range of like my K list length, which is 3, right? And then the K will be in K list. So it's kind of like a simultaneous or parallel loop. So in this case, I can just write it this way for K I in zip. It's called a zip. It's just like a zip we use in K list, and then I is gonna be in what? What is gonna be in the range of the length of K list. So here, of course, the length is 3. So I is gonna be 0, 1, and 2. So here now I can create the what? The figure here. I'm gonna say here I can create it, but before it, sorry, my fault. Before to choose, I need to give me a second. I need to make this one first to fit it. And then here neighbors, instead of 1, I'm gonna have neighbor equal to k, mono.fit, right? And then I'm gonna create this one, y predict equal to this one, mp x1 x2. So now after this, I can do this finally, yes. Because here I'm gonna plot, let me see, I'm gonna plot these, and then let me see here for ice figure. So now here I can just plot oh, here we go. Plot the generated training data here. So I'm gonna still have x1, x2, x3 here. And now I'm gonna what? I'm gonna make the PLT dot P color mesh. This one here, color map here. And then I'm gonna what? I need to have a title. Yes. X dot set title. Let's say it will be K equal to K. PLT.legend, PLT dot show. Okay. And don't forget one thing. Here you have the K this, but you'll have the I in we want it. Here I already have it. So yes. So I guess I can just do it. It should be correct. Oh no. Let me see which one is wrong. 37. Y2GI is wrong. Let me see why this is. No, must be integer between 0 and 0. Okay, okay, okay. So if that case, I need to make I plus one. Sorry, because what? Because I in range is gonna be 0 to 3, but here it's gonna be 1 to 4. Here we go. So okay, here we go. Now you see why I want to make it. Oh, wait, wait. That's the reason. Forgot the last thing, which is a legend. That's why only the last one has a legend. Actually, the legend. So here we go. Okay, here we go. Uh, Now you see why do I need to add this to make it like a GUI because it's so small. I can just make it bigger. You see what I mean? And I just want to make sure that I still have figured out the title layout, but it's a very not a big deal. Title layout is just to make a setting of everything, the layout tight and comfort, make it look more comfortable. But honestly, this is already, at least for in my view, it's already good enough. So we can clearly see that we, first of all, the training data are exactly the same training data. I mean, exactly means in one run, these are four, thoughts. And but the decision regions are different. So we can see that when k is small, what did you see here? When k is small, you can see it's kind of like not that smooth. You see, it has a lot of those kind of like the sauce here, like sauce, and also those kind of island, and then you can see from k equal to 5, similar things. It has those kind of zigzag and a sauce here, and then this point is a special point you can see. However, when k is bigger and bigger, it's more and more smooth. You cannot see those kind of islands anymore. Let me make another extreme case. Let's say k equals to, wait, how many training data I have totally? Oh, I totally have 20 or 50 already, so I cannot make it bigger. But let me run it again to see another case, another result. And similar things. You can see when k is 0, we have an island here with a, why this one is, oh, because here you can see if you make it bigger, here is a red point covered by this blue point. So that we have those islands. Even k equals to 3, we have an island here and a lot of source zigzags here. But when k is 20, you can see it's much smoother. And actually, this is a general phenomenon. It's not limited only to this specific data set. And so the general conclusion is here that uh, a small value of k produces more jagged classification boundaries characterized by numerous small islands, as we can see here. Oops, sorry. As we can see here, no, I can use the one I just showed. Islands and the jagged, we have those kind of source, shaped here. And by comparison, as k increases, these boundaries become progressively smoother with fewer isolated regions. So this is the thing. And more formally, it's actually somewhat like, we call it a bias and a bias trade-off in variance bias and a variance trade-off in statistics. It is like a smaller k tend to result in a higher prediction variance, leading to a greater risk of overfitting. Meaning that, well, if you use a very, very small k, let's say k equals to 1, you may get something, the result of your fitting is great, perfect, like uh, but it will be kind of like a lower bias, which means it can yield more accurate predictions on the training data. That's it. Conversely, if you make the K larger, well, the training prediction, the training itself to the training data itself, the prediction may not be as good as a small K. However, it will lower your risk of overfitting. So we call it, like selecting the hyperparameter K involves a fundamental trade-off between the bias and the variance. Actually, I believe I have this extended reading here. If you see the lecture of the lecture number 6 here. Here we mentioned something here and also some statistical views. If you're interested, again, it's absolutely not required. I wrote it many years ago, actually, and also it's mostly based on a textbook. I should be very clear about this. I mean, I just changed different things and I also refer to several different books and I made them together. Or another method is you can just open this page and then it shows you something more details about the trade-off between the bias and variance if you're interested. Okay, so here are the things about the simple applications of KNN. In the following, we're gonna mention a little bit. Trust me, it can take you hours of hours if you want to make it deeper. But here, just very, very small example, very little things about the KNN classification in images or applications in images. So first of all, KNN is the K nearest neighbor. When we say nearest and the neighbor, we mean it is distance-based classifier, right? And we need to define the metric. Excuse me. We need to define the metric so that we can say distance. Under what metric you're talking about distance? So in all those examples, the distance is simply what? The distance is simply physical distance or Euclidean distance, or you can say L2 norm, the same thing, which is just, we see from all the points how far it is. If it's close to my k-nearest neighbor, so I'm going to classify to this. This is the distance, which is a physical or Euclidean distance. However, be careful when we're talking about images in many, many applications, what we mean, the distance is not the absolute like Euclidean or physical distance. It can be the color distances. So for example, here I wrote, for instance, in many image-related problems, each data corresponds to a pixel represented by its RGB data, red, green, blue data. I assume most people here are familiar with RGB. Like for example, you can see my screen. It is like each screen is composed of I don't know how many m by n or a by how many pixels. My resolution here maybe I actually don't know 1980 by 1020 maybe, but it's just how many rows and vectors, also rows and columns of the pixels. That's it. So instead of using the physical pixel to pixel distance, classification can be based on the RGB to RGB color distance. In other words, here, when I'm talking, so each RGB vector consists of three components, R, G, and B, meaning the red level, green level, and the blue level, right? It's between 0 and the 255 integers, Okay, so if I give you 2 pixels, the RGB of the first pixel is R1, G1, B1, and the RGB of the second pixel is R2, G2, B2. So if we define the RGB based distance, I'm going to compute the distance between the 2 pixels in this way. You see what I mean? Here, it's no longer based on the physical Euclidean distance. Instead, it's based on the color Euclidean distance. So, and here, hence, under this metric, the k nearest neighbor becomes the color similarity rather than the physical similarity. So this is the very, very first thing I want to mention, how we apply those kind of, KNN in images. The very second thing is the pixel recoding. So people may say, hey, it's just so good, I already have this, so I can I can compute something be based on this. I do the KNN. True, you can do it. However, in many cases, we want to smooth, you know, I want to smooth the image. Why? Because in some cases, an image could include some noises. By some smoothing matrix, I can try to eliminate those kind of noises. Under it, like I mean, this is actually more widely applied in neural networks. But since here I'm not going to introduce neural networks. Uh, let's show a very super simple example, which in which the smoothing matrix is the ones matrix. Or let me use a even simpler language, which is so suppose number five, this pixel is my target pixel. What I'm gonna do is I will consider all the adjacent matrix or the adjacent pixels, and then I will recode the RGB of my of this pixel by the mean of the RGB of all these 9 pixels. So this is the so-called smoothing matrix applying by the one matrix. Or yeah, you actually don't you care here. Since we're not introducing KN, not introducing neural networks, you don't care what does smoothing matrix mean. You just need to kind of understand it as I try to smooth the picture, the image. I try to make it more like somewhat to eliminate the noise, and hence here for each pixel I want to recode the RGB instead of directly using its RGB. I'm gonna make take the mean of all the adjacent RGBs to be its RGB. Of course, the mean includes itself. So here I have totally 9 pixels, and here the value of the recoded value of the RGB of this pixel number five gonna be the mean of all these of all these 9 pixels. So this is one method to recode it. There are actually many methods. Another method is I can even, instead of compute the mean and finally I'm going to return an RGB, which is a 3 by 1 array. In terms of this, I can just, you know, consider all these 9 RGB values. And you see each RGB value is a 3 by 1 array, right? And hence, for each pixel, instead of save only RGB, I mean 3 by 1 data, I'm going to save all these 27 by 1. So, of course, this will make your further computing or further analysis probably more accurate. The bad point, however, is that your storage is going to be 3 times because, no, sorry, 9 times, not 3 times. Originally, for example, here I just have for pixel one, I just have RGB done. But using this method, concatenated RGB vectors, I'm gonna say for R1, B1, RGB, R1, G1, B1, R2, G2, B2 until R9, G9, B9. So it's gonna be 27. You can do it, but here I personally would prefer using a smoothing matrix, especially like all one matrix. So in this example, we'll use this way so that we will recode for each pixel and we will get a new matrix. Be careful that, for example, if I consider pixel number one, it only has one, two, three adjacent matrices. Why? Because you cannot make the index beyond the board, right? And hence, when we are writing the code, we need to consider the case. What if the target pixel is on the board or at a corner? What's going to happen? For example, like on the board, let's say pixel number two. I only have how many neighbors? One, two, three adjacent pixels. One, two, three, four, five, including myself, only six. So I need to consider it. Okay, so let's do an example. Here is it's just a screenshot from Google from Google Map. By the way, it was done 4 years ago, probably. I believe that was right after post pandemic. I remember, but at that time I was teaching in North Dakota State University. I just realized that they actually they updated. You can see the image is way more beautiful, but the school basically is still the same. From here, you can see this is like I actually forgot what is I forgot what it is. Sorry, it's a department. Some buildings, and I can see here. It's right here. The colors are way more beautiful. I haven't, kind of extract data here. If I do it maybe next year, if I do it again, I guess we can get a much better training results, which is right here. But let's continue using this one. And so here, it's just a very baby example. So what I'm going to do is that I will classify the terrain into four classes, which are number one is building, number two is the parking lot, number three is trees and the grasses, number four is street. So for example, here, around here is going to be parking lot. Those kind of things going to be building. Those green things are trees and the grasses, and then finally those things are street. So of course, I mean, by observation, we will directly say, hey, these are the trees. Why? Because it's more green. These are kind of like streets. However, it may be difficult to differentiate by your eyes. Streets versus parking lots. Here we want to write a code to use KNN to direct automatically show us the result. Okay, so first of all, the data are all here in the lecture folder. It's lecture 6. And then oh wait 1 minute. Why I have two here? Sorry, let me remove this. No. Uh, so this is the data. Oh, I know why. I forgot to put the image here. Sorry, my fault. Replay. What? It already exists. Oh yes, it's here. It's here. Yeah, it already exists here. So when you're training, when you practice at home, you can just do this to train it. And then what you're gonna do here is to oh wait 1 minute. What did I do here? Oh my goodness. Sorry. I just realized I didn't create a lecture. Seriously? Lecture 6 and then K. Okay. Oh, let me first save it. Let me close it and then let me drag it to lecture 6 folder. I forgot to create a folder. Great. So let me see. Let me just restart the kernel. Sorry about it. Okay. Otherwise, just in case something's wrong. Okay, so now it's here. And then let me just put it like this way. Okay. So now let's see how they do it. I believe, yes, I separate into many different steps here. I mean, since it's the very first time we handle in this class, we handle those image-based classifications or image-based things. So let me do it slowly, I mean, in different cells. Although when I made the slides, I did, you can see the numbers I did in one cell. But when I show it in the class, I'd better make it to be different cells to make, to decompose the steps. Okay, so first of all, what we need to do is to import those things. I can just save time on my paste. Import those. I will import more things for sure. For example, I know for sure I will need to import pandas as PD. Okay, but let's see. I mean, gradually when we need it, we can just import new things. The first step is we need to read the original image. So I'm gonna here read the original image. I wrote those lines is just to indicate different sectors. You can definitely, for example, oops, wait, why? Oh, wait, because of this. Yes. You can definitely make it to be, let's say, you can write it this way. For example, you can make it to your bar down and then you make it read the original image. You can definitely do it like this way. But here I'm just, lazy so that I write a comment inside. So to write a comment, to read the image, first of all, I need to create a figure. PLT.figure. And now I'm gonna use something called PLT.im read, which means image read to read the image. So I'm gonna say image equal to PLT.im read, image read. What's the name? Oh, sorry, I forgot. Yeah. I need to put this into the folder and also the training data, which is here. I need to move the string data here because later we will use it for sure. Okay, so now I have this image and the train data. So I'm gonna first of all rename control.jpg. So I'm gonna read it, and I know many of you will be very curious. Hey, what does this image? Because you write image equal to what does this image tensor, let me temporarily call the matrix look like? It's actually a tensor instead of a matrix. Okay, see it? It is in this way. And you can see why it's a tensor because it has each cell is an RGB, RGB, RGB. And then to make it more clear, instead of showing in this way, what I'm going to do is this. So I will write this image tensor to a .csv document. Then I will open it. Then I will observe how it looks like. So here, what I'm going to do is I will use something called with open. I'm gonna have image CSV.csv. Oh, wait, did I name it this one? Yeah. And then I will have a parameter W, which is means write, to write instead of to read. And then I'm gonna have a new line. That means, in each line, I don't need to add something there, and then as file so that now I can have something file writer equal to CSV.writer. So I'm gonna write what? I'm gonna write this file. This file means this file. And then delimiter equal to, I believe I forgot the space or comma, comma. So comma means between two different data, it will have a comma here, dot comma. Okay, so now I will have file writer dot write rows because I'm not gonna write one by one. I'm gonna well, write rows. I'm gonna write it directly by rows. Why? Because I've already had this image tensor image, and then let me just run it, and then it should create. Oh, it's so fast. Well, wait 1 minute. CSV is not defined. What do you mean? Okay, sorry, I forgot. That's what I'm saying here. When to import this CSV, this is something, a document, a library for us to handle those kind of reading, writing CSV documents. So here from, no, it's just direct import CSV. Sorry, let me just make sure. Yes, import CSV directly. That's why I'm thinking, yeah, okay, here we go. Okay, here we go. And then we can see this one's already been made. Okay. And we opened. You see, now you see why I call it as a tensor. Because what? Because that's so weird. I put a new line to be empty. Why it still doesn't? Never mind. Otherwise, I can have a header, a head here, but it doesn't have head. You can consider it like index 0, and you can see it has how many. I can print the shape. Let's say print the shape, the image dot shape. Hmm? Why don't print the image of shape? Okay, that's a bit big. So, I know why, because I show this. I wanted to read the image as well. But why don't show the image? That's interesting. It should show me the image. Uh, anyway, but the shape is 320, 670, and a 3. Yep, that's why I do need to see the image because I will tell you what does it mean. Let me just rerun it again. Sorry. Sometimes maybe the server or something. It should because it should perfectly. Huh? That's so weird. Give me 1 second. Let me just save it. We'll probably need to restart the kernel. We probably need to restart everything. Restart kernel. Okay, and then to make it safer, let me completely just refresh the whole page. Yeah, it could be due to server busy because technically it should directly show me the server. So the server should directly show me the image. Sorry, here. Okay, then let me just actually I don't have to make this since I've already have this. Let me just directly show it. Uh, Okay, I know why. Sorry, my fault. I should have, yeah, I must, yes, I should have this line, plt dot image show. That's why. Sorry. Okay, now I should show you. Here we go. Sorry about it. Okay, so here we see 320, 670, and a 3, right? Okay, now let me show what that mean. And you can see here, see this area, I have the XY indices, right? Let me make it bigger. And I have this axis on purpose. And you can see if I put this corner, see it? It is something, and don't forget it's 320, 670, and 3. This is actually the row call the total row column number of my pixels. And oops, it's just let me just I cannot make I cannot make it right to that specific corner. But just to let you know, it does include 320 rows, which is the rows here 320, and the 670 columns. In other words, this image CS dot this is image CSV dot CSV. Each of these number, including the head, which is index 0, each of them, you know what, is the RGB of the pixel. So for example, here it is, let me just choose here. It is the one, two, three, four, the fourth row, 11th row, fourth column, right? Let's go back. 11 and the 4, 11 and 4. How can I find it? Which is the fourth row, fourth row. It's just, very difficult. I can actually to show, let me just print. Let me use another cell because I don't want to read it, do everything again. Print, let's say image, uh, let's say 100, 100 for example. You see it? It shows 178, 178, 166, which is right here. 100, 100, and actually I don't know which is 100, but anyway, it will be one of the cells because I don't have a column number here. I mean, that will be the same. So if you put, look at here. If you put the XY to be 100, 100, Y should be bigger. It's around here. Okay, 100, but Y want to be 100, 100, 100. Okay, here we go. Okay, here we go. And did you see it? 178, 178, 166. See it? What I mean, this area, see it? I move it. This number should fit this number if you go to, I mean, to save some time, I'm not gonna do it again. It takes a lot of time to get it. But each of these, data is a RGB data, shows the RGB of the corresponding row, column, pixel. Okay, that's what we did here. Of course, one thing I do want to mention is that so these are not necessarily in practice. The reason I write it is just to, since this is our first time to handle those images, it's just to show you what does the tensor, look like. That's the only reason. Okay. So first of all, we read the original image. So we have a like very fundamental like observation of it. After it, remember, what did we say? We need to recode the pixel, right? To recode the pixel, we use the mean of the adjacent pixels. So what we can do is here, let me just remove this part. I will recode the image pixels by the mean of all adjacent pixels. Okay, so I do this one. First of all, I need to create a new tensor. My original tensor is called image. My new tensor is called, for example, image recoded. So first of all, I need to create a zero matrix. Of course, you say, why I create a zero matrix? Why don't I create a one matrix? You can definitely do it, but they're the same meaning. Meaning is that I will create a matrix with this size first. So I use np dot zeros. This is just to create a new matrix, the zero matrix, and then image dot shape. This means this zero, the matrix, the shape should be the same as image recorded. Okay, so now I will do this for the whole image, right? So I will have loop for I in range of image dot shape 0. This means for rows, and then for j in range of image dot shape 1. This means columns. What I'm gonna do is first of all, I will have RGB equal to zero. Why? Because I will sum all the adjacent, adjacent RGBs and then divide by the total number of neighbors. You may ask, so why don't you divide by nine? Because you never know it's nine. For example, if it's at a corner, it has only four neighbors. I mean, four elements, including itself. If it is on the board, not a corner, then it has three. If it's in the center, most other normal pixels, it has nine neighbors. And hence, I do need to create a zero RGB and make it a plus plus. And then I will have total uh, adjacent pixels equal to zero. This counts the total number of adjacent pixels. Okay, so now think about it. At most, I can have nine pixel. I can have nine neighbors, right? Which is like, I mean, nine means including myself. Okay, so suppose this is row ij. So this will be j minus 1, j plus 1, right? And column j minus 1, the column j plus 1. And here, this will be row j I minus 1, row I plus 1. And hence, here I will write another for, which is for row in, let's say I minus 1, I plus 1. By the way, this ij is, the for loop ij, okay? And then for, let's say, column in j minus 1, j plus 1. I believe there are some quicker NP methods to handle it. But here I'm just lazy to find it. So I already coded by myself. So here we do need to consider those row, corner or board issues. What I'm gonna do is I'm gonna here write an if statement, which is among all those, I minus one, I plus one, and the j minus one, j plus one. If it is a valid row or column number, then I just use, RGB plus the corresponding, I mean the data I got from the image, the image corresponding RGB. If it's not, I'm not gonna plus. So what I mean is, so for example, suppose we're gonna, this is our target data. So you can see this one, two, three, four, five, six, seven, eight. All these eight are valid, right? And hence I can, plus sum up all these, red, all these green, all these blue, and then divide by the total number, of course, including itself, okay? And then divide by all the number of adjacent, the so-called where it is total adjacent pixel, and then I get the average. However, if my target data is here, so let's say here, so I only have one, two, three, four, five, including myself, six. And why, for example, I cannot consider it here because it's nothing. You're already in the board. So in this case, my column J minus one will be invalid, you see? And hence, if this is invalid, I'm not gonna add. And hence, I'm gonna write an if statement in this way. If row is between zero, less than or equal to row, less than or equal to the image dot total rows, which is image dot shape zero. Be careful, need to be minus one. Why? Because here I'm going to make it to be plus one. So the maximum should be this one minus one. So plus one is equal to itself. And also the same for column. Column is less than or equal to zero, greater than or equal to zero, and less than or equal to image dot shape one minus one. If this, that means it's valid. And hence I have R plus equal to image row column zero. That means I'm gonna add the red, and then you can do the same thing for green and the blue. R plus plus, G plus, and then B plus. Okay, and don't forget, finally, I'll need to compute the total adjacent pixel E plus equal to one. And after this, be careful, this the indentation gonna be here. Parallel with this one, I'm gonna create image recoded. Image, wait a minute, is it correct? Image, yes, image recoded ij equals to what? Equals to the mean. Now here I use integer division because RGB value, it must be an integer, it cannot be a float. Total adjacent, and then B G, and then B divided by. Okay, here we go. So in this case, I can create, this one gonna be the smooth like tensor by the mean of the adjacent all the adjacent pixels. And finally, some more things. I can what? I can write this, and I can let me just copy and paste to save my time. So that I'm gonna make it to be image recoded CSV.s, everything blah 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 here, and the read write rows, and it's gonna be image recoded instead of image, and then here I can print the image. Oops, I can print the image recoded shape. Okay, there should be a new document here. Wait a Okay, here we go. Image. It takes some time, you can see, because we have four I4J. Okay, so here's the image recorded. Let's have a look at it. We can, for example, do a calculation. So, for example, let's consider this pixel. So, according to where it is? Huh? Wait, how come it's so big? Wait a minute, wait a minute, wait a minute. I'm afraid I did something wrong here. Wait a minute, wait a minute. 000. Wait. Then how come this number is so big? It should not be. It should not be that big because I have, let's say my image one equal to. Let me have a look at it. Probably something's wrong here. Or equal to this. Wait. 0, 1, 2. That's so weird. Wait a minute. Let me open my local doc. What? I could have made a mistake somewhere. Similar. How come this is 135? It doesn't make sense. It's 135. Let me see. Why feel the image, the tensor is something wrong? Give me one second. Oh, okay. Wait a minute. I know why. Sorry. Guys, I'm afraid that the issue is from here. The issue is from here. Oh, okay. It doesn't have a column number. That's what scared me. Okay. It's all correct. All correct. Yeah. It doesn't show the column number. Just now, my screen was like this way. That's why I'm thinking, how come? Sorry about that. Let me see here. Let's say, let me see here. The zeros, I mean, the column and the second. So let's verify. So this pixel has what? So sorry, no, this one. These are the neighbors, right? Let's just consider the R, which is the first, element. So I have 178, 181, 180. Let me just, I'm gonna summation 178, 181, 180, 178, 183, 183. Okay, and this number divided by 6, it is 180.5. Don't forget that I have the what? I have the where is I have the integer division. Integer division pushes to 0, and hence it pushes towards 0, and hence 180.5 becomes 180. And hence you can see, oh sorry, I can close it. And hence you can see this one, the first data here, 180. See it? Similarly, you can verify, for example, the second one, it must be 181. The third one must be 165. That's the reason. Okay, so now we have already got this smooth or recoded image tensor. Again, these rows are not necessarily. I mean, the reason I show it is just to show you, the calculation of this. Of course, those kind of center points is going to be easier because centers just, all of this nine. The difficulty thing would be the corner, those kind. I mean, this one, corners, and also those kind of, borders. That's gonna be the thing. Okay, so after recoding, uh, the image tensor, what we can do is actually we can now read the training data and then do some training. Okay, first of all, let me just show you the training data. What does it look like? It has three columns. So the last column is the label or class. The first and the second column records the x and y, which is the pixel actual location. So that means, let me have a look here. That means pixel row equal to 182, column equal to 70. The class is one. Class one is what I forgot. Class one means building, so that we can verify, for example, 285 and a 70. It must be a building. So let's go back to the where it is. What's the number again? I forgot. 270, 285, 70. Okay, so let's go back. We need to see here, okay? 285, 70, 70, 70, make it smaller. Oh, 70, 285, 285, oh, maybe 285 is around here. 70, make it smaller. 70, 285, oh, and 70. You can see that indeed. You see this area, this point is a building. This is clearly a building. I can make it bigger. See, it is around here. This is clearly a building. And the similar things, you can have all those kind of, coordinates corresponding to, let's say class two is the parking lot, class three is trees and grasses, class four is streets. And you can see all these. Okay. So now I have this training data. However, be very, very careful that our nearest neighbor distance here is the RGB. And it's not those coordinates. This is just a coordinates. And hence, what we need to do is we need to read the coordinates, from the training data, and then go to the image tensor to read the sorry, not image, the image recoded tensor, because we need to recode it. Recoded tensor that we just did in this cell to read the corresponding RGB and use the RGBs to train the KNN classifier. Okay, so what we can do here is, I forgot, I don't know, give me a second. Let me see, load the training data. Oh, okay. I'm gonna first of all get a tensor train. Here I'm gonna load the training pixel or training data, doesn't matter, the same thing. Tensor train equals to pd dot read CSV. So I'm gonna read this training data. Rename, okay. Okay, then what I'm gonna do is, first of all, I can get a Y train. That's a Y train, which is the label, right? I can say tensor train. The name is, what is the name? Class. The name is here, class. Okay, Y train class. Okay, be careful. I cannot have this one to be, if you write this way, it's gonna be wrong. It's not this is wrong, okay, but I just, you know, remember before we say, okay, okay, tensor dot job, and then I'm gonna say, okay, job class. It's so simple. X is equal to 1. If this is the case, and then I make that's a model dot fit X train Y train wrong. Why? Because what is your X train if you write it this way? It is coordinate. It's not an RGB. And hence, we need to do one more step. Here, I just write it to be X train row column probably. Let me see. Where's my, yeah, I name it to be X train row column. So, sorry, X train row column, because this records only the row and column of it. The true X train need to be translated by the corresponding RGB. So to this end, I first create a zero matrix first, np.0. It's going to be the shape of what? It's going to be the shape of X train row column, right? Because this shows me how many, rows, columns it's going to be. It needs rows, and then because it's RGB, hence the column number should be 3. Okay, now I can have ready to fill this X train, which is 4i in range of, let me see, it should be the shape zero. The train dot shape zero, meaning the row call the number of rows. For here, I'm gonna have row equals to, here we go. I will read the row of this one, right? Training here, it's gonna be the I log zero, sorry, I zero, and then column equal to x train, row column dot I log I1. Okay, and what I'm doing is this. I'm gonna read for ice. The row is 54, for example. The column is 308. Okay, now I know row equals to 54, column equal to 308. I'm gonna go where? I'm gonna go to this matrix. This one, I mean, this one we just created in the previous cell. I'm gonna go to this matrix and get a true training data I equal to image recoded here, row, column. You see what I mean? Because here, let me just give you an example. Let's say here, let me just find a small one, let's say, you have a small one. Let's say 270, 44. So I know row equal to 270, column equal to 44. I'm going to go to this image recoded CSV. So I'm going to go to row equal to 270. Where's my 270? Why it shows I don't know, looks like I mean, inside it just show, let's find a smaller number. Let's say row is 111, column 32. Okay, so row is 111 is here. Column 32, I actually don't know where's column 32. Assume, okay, assume this is column 32. Then you see what I get here? Training data x equal to this x image recorded row column. And hence training data I will be equal to this value, which is 133, 132, 107. And this is exactly what I want because our k nearest is based on the color. The distance is based on color instead of physical distance. Here we go. So now I have what? I've already loading the training data. Next step is what? Simple, right? I can do the classification and then plot the decision region. And I believe, yeah, I have another cell. So let me have a look at it. Yeah, KN classification. So here, now I can do this KN classification and decision regions plot. Okay, so now first I can generate, remember the Nash grid. I have X, X, Y, Y here to make my life easier. I just make it a X. Be careful, don't write big X, okay? It does differentiate it lower and uppercase, MP dot link space. And then here, start is 0. The upper bound of it will be image dot shape. Be very careful here. Since here X is what? X, you can see here, let me just cover it. Oops. X is this. So X is actually the number of columns. This is gonna be my X. My true X should be like 670, the width of this. So it will be shape 1 instead of shape 0. I have, give me 1 second. Wait, did I use -1 plus or -12? -1. The reasons because, yeah, because it just starts from 0 instead of start from 1. So it will be 0 to -1. And how many points you will generate for each pixel? I will generate 1 point, and hence it will be image dot shape 1 directly. And do the same thing for y, but make it to be, the other one. Instead of shape 1, it will be shape 0. 0, and here will 0. Okay, now I can just xy equal to np dot mesh grid xy. Okay, so now remember we can do what we have the. Oh wait, I probably need to load something similar. Did I load? Oh, I've already loaded. So now I have a boundary map. I have the boundary color equal to this listed color, and then I put what color I forgot. Rose brown, light, steel blue, pale green, and orange. Okay. Rosy brown. You may ask, so where did you get it? Simple. It's from the web page. It's oh, where it is. It's the color the for list of the name the color. So I got all from here. That's where I got this. Anyway, let me see here. I forgot it again. Sorry. It's the what is the rose brown, light, steel blue, pale gray, and orange. Okay, here we go. Rose brown is light steel blue, pale green. The last one is orange. Okay, I have this boundary color, and then we have we can do something as what we did here. Remember? Where am I? I should be here. Uh, this one is just this one, just this one, 2 by 2 subplot, because I just restart the kernel. That's why it didn't run again. So I can do something just very similar to what we did here. So I can create a figure equal to plt dot figure, and then I will create one subplot ax equal to the subplot. However, here what we did was we directly write the first plot inside because it will be one of the k list, which is k equal to 1. But here, what we want to do is I want to show the first image as the original image. And hence, I want to plot, subplot when I equals to 1 independently. And hence, I want to make it here. Another thing is later we'll see the y. It can be something like a reverse. But anyway, let me show you what I'm talking about. So here I will first create the original figure, which is figure dot add a subplot 2 to 1. And this is nothing but I'm just image show image. And then here I will set a title. Let's say original image. Okay, oops, sorry. Okay, so after it, let me make sure I'm correct. Yes, correct. And after I will make I equal to 2 and make a k list and make something here. You can definitely do the same thing, like for ik in zip of for ki in zip of k list and the length of I. Here I just try to show another method without using zip. Then I'm gonna have in the end because it's in for I'm gonna have I plus equal to 1. Just to show actually this method is not as good as the method I used the zip before. Here zip you can see make it easier actually, but I mean try to use different ways to show something different. Okay, so where we're here. So now I will have I equal to 2. Why? Because I will start here this number to 2, and I will create a k list equals to what did I use? 135 maybe? 1 5 10. Okay, it's here. I use k list at 1 5 10, and then for k in k list I'm gonna do first of all, let's make it a classification model equal to k nearest neighbor, and neighbor equals to k. Okay, then model dot fit, and then x train. Remember, we spent a long time in the previous cell. You got x train and then y train, and then I can do what y predict, right? To predict for each point, which I generated for x y equal to np mesh grid. And this one equal to model dot predict. And then remember what you need to do, np dot array, and then this dot t to convert it. And this array will be okay. Be careful. This array will be the this recoded matrix. I will put for all the columns and the rows. But the first one will be the red color. The second one will be the green color. The third one will be blue color. In other words, I'm gonna have here as image recoded all columns, all rows, but here it's gonna be 0 instead of all dot ravel. Again, ravel is just to make it flat, and then I can just let me copy and paste because otherwise it's super easy to make a mistake here. I remember when I prepared the lecture, I made a lot of mistakes here. To transpose. One trick is if you think it's too long, you can write in this way, make a slash, and then Python will understand to connect these two lines into one code. I believe I did it. Yeah, I did it here. You can see this one in my slides, but since we're just showing live code here, so I don't have to. I just make it to one line to make my life easier. I just want to make sure everything's correct here. Yes. Okay. So here's my y predict, and after it, what will you do? You can plot, right? So x equal to figure dot add a subplot. Okay, so 2 to I. And then I'm gonna have one minute. Uh Oh, okay, okay. Here's one very important thing I believe here. Yes, I can definitely directly use this x dot p color mesh this to show. The issue, however, is that it will make the zero axis to be here instead of here. To make it in this way, I wrote it to be x equal to image show image. So this is to let Python know I'm going to go to the image mode. And hence, you need to make y equal to 0 here on the top instead of at the bottom. No worry, let's first include it and then we will remove it, rerun the code. You will see what is the difference. X dot p color mesh, mesh x y predict. Be careful here, we need to reshape with x dot shape and then CMap equal to the boundary map here. And then I need to just do this set title. It's gonna be, let's say, k equal to k. And finally, don't forget because you didn't use a zip, so you have to manually I plus equal to 1 and final PLT dot show. Okay, here we go. Then y y predict what is wrong? Invalid syntax. Y predict equal to model dot and why this is wrong? Let me see. Did I create anything wrong? Model dot predict probably those kind of parentheses array will met here is recorded one dot ravel. Yeah, looks correct. Why? Oh, sorry. I know why. It's here. I accidentally include this one, and hence Python consider these two lines to be the same line. Hence, it's wrong. And oh, one more wrong. Great. K list is not. I did. Oh, okay. That's something I really hate to. K list. Okay, here we go. X train is not. I just defined X train here. What is wrong here? Model dot fit X train Y train. How come X train is not defined? So what is this X train I? X train defined here. That's so dumb. Let me rerun this cell to make sure that it's uh-oh. Okay, wait a minute. I'd better rerun everything. It may be because I restarted. Yes. Just now I restarted kernel. Sorry about it. So I need to rerun all the cells again. Sorry about it. Let me just let me just rerun the cells. I start from which line here? Okay, so that I have this, and then I should have the image record. Wait. Why this one is? Oh, I know. No. It's not because of that. I should run this one first. And then extra I equal to why this one is wrong. Yes, I should have this. Yes, this one gets this print. Okay, so this one is done. Now I'm gonna run this one. Let me just make sure extra equals to answer. That's why. That's pretty dumb. Then how can I pass this one? Interesting. Why? No. It's correct. Here's why. X is here. Tensor train. That this one row column is here, and then I'm gonna have let me have a look at the code just in case something's wrong. Okay. Here as well. Dot shape. Dot we want to extreme. This is zeros. Yes, dot shape 0 instead of 0. Okay, now it should be correct here. Hope so. Which is this one. Let's wait a little bit. Let it get this one X train, and then let me just print X train to make sure everything's correct. Yeah. are required to print it. Okay, yes, this format is correct because it is in each one, it is what the RGB. Okay, now I know already, I've already got a string. Then I'm gonna run this code. It should be correct now, unless some other mistakes. Yeah, it takes some time because the pixel is pretty large. Let's wait a little bit for you can see it is the kernel is actually running currently. But I can let you know this is the result. This can show this is the original image, and this is the case for k equal to 1, k equals to 5, k equals to 10. Let's see when it's done. Okay, it's done already. Great. Let's make it bigger. Now you understand why I need to add the magic thing here, which is matplotlib IPyMPL, because this can make my view much bigger. Otherwise, it's going to be just pretty small. It's not comfortable. Just okay, and you can indeed. Wait. Why it's k equal to k? Wait. That's that's really dumb. Oh, I forgot this f. But anyway, no, not a big deal. Just to let you know that because I don't want to waste the time to run one more time. This is 1, this is 2, this is 5, and you can indeed see from whole my the orange. So this dark color. Let me see my map. Rose brown is class 1. Class 1 is what? Class 1. Class 1 is my building. Class 2 is the parking lot. So this is the building. This is the parking lot. Wait, light steel blue. Yes, this is the parking lot. And the third one, pale green, is the green things. And the first last orange is the street. And you can see when k equals to 1, there are a lot of noises indeed. And why? Remember, it's kind of like a bias variance trade-off. It is kind of like overfitting based on these training. I don't know how many training data do I have. Well, 264 training data. Uh, then when k equals to the last one is k equals to 10, the result becomes much smoother. And huh, actually, do you realize there's that problem? Oh, however, it's a mistake, but to be honest, I didn't make this mistake on purpose. However, it's a great mistake because it shows you the great thing if I don't use this. Remember here, I said I need to use image show, right? Otherwise, and you can see here, the y-axis here, because Python knows this is image mode. So the y-axis is here, it starts from 0. But if you see here, I didn't add this code, which is x. I should add one more here, which is x equal to this. Then these 1, 2, 3 pictures reverse, which is so this is 300 corresponding to here. So I probably have to rerun it. Otherwise, the result is just too bad. But to save time, we can use here. What we do here is that we can see when k equals to 10, the result is actually smoother. Compared with here, we can see indeed these are parking lots. These are streets, although here are not that clear because streets and parking lots, remember here we do RKNN based on the color. You can see actually, let me make it bigger. How to make it bigger here? You can see the color of streets versus the color of the parking lots. They're pretty similar. I don't know how about a new Google map. Do they make it similar or just, let me see here. Let me open the Google map again. I bet you if I do the training now, it would be way better. Why? Because because you can see those kind of parking lots, it has those kind of lines and have some those kind of yellow color. While those kind of streets, the color is very pure. You see what I mean? Like here, the color here, streets, parking lots, they have those kind of yellow, those kind of points. As long as we can extract those kind of things in the training data, then it should be able to capture. It should be smart enough to capture those yellow things and recognize as the parking lots instead of the streets. However, in this picture, my training data, you can see the colors are pretty close. However, even if this is the case, still you can still you can see the result is not too bad. Honestly, the buildings and also those green trees and the capture of these are pretty good. You can compare these with this original data. However, the performance of differentiating the parking lots versus the streets is not that good. Let me see whether it runs. Yeah, we've already got it. Now we see the point here. After adding this sentence, first of all, we corrected k equal to what because I forgot to write the f here. The second thing is after adding this line, it knows it's the image mode, and hence y equal to 0 is here instead of being at the button. Okay, and this result, you can see indeed k equals to 10, the result is more smooth. You can clearly see it. I'm not sure what if, let's say, what if I add a, let's say, what if I add it this way, 1, 3, 5, 10, 20? I guess it will be even smoother. But yeah, it will be similar things. But the truth is that with the increase of K, the result will be more smooth. However, the training the training accuracy will be lowered. But at least you avoid the risk, or you are lowering the risk of what? Lowering the risk of overfitting. Okay, finally, as a summary, basic summary, image classification, those target object classifications are pretty important because after this classification, we can extract and analyze a wealth of info from the image. So for example, we can calculate the average, the area covered by those kind of trees, this greenery, parking lots, and a building on the campus. And we can use those info for the facility plan, layout planning. And for example, like if I want to build an area, I want to plan and I want to see, hey, how large, the greenery, the size of the greenery is. And we don't have to really, do it by our eyes. We can just use this simple, super simple KNN algorithm to do it. And all, of course, with more detailed data, for example, including physical locations. Don't forget here, I'm just running the KNN based on the RGB distance. However, we can add a weight. I guess it may appear in your second homework, and I can include the distance, the physical distance into the metric. In other words, it will be a metric including both RGB and also the XY location. Then we can significantly improve the precision of the predictions of those buildings, parking lots, street names, something. We can add a lot of things there. And there are also some small things, for example, like object rotation, scaling, those kind of variations. If you're interested, I believe I showed here in the, oh, sorry. I showed here in this as well. Oh, why shows error? I know why. I know why. Because of here, I just changed here, but I didn't. I changed the neighbors here. I plus one. Sorry, it should be 2, 3 instead of 2, 2. That's why it shows it's beyond the boundary of the one from 1 to 4. That's the thing. So if you're interested, we can have a look at the where you can see this sign is still running. Let it run. You can have a look at extension here. For example, I believe I introduced a method which is a tangent method here. This tangent method can, efficiently solve those kind of rotation issues. And also it includes something called curse of dimensionality, which is in some cases, if you brutally run KNN, you may suffer a situation that you don't have enough data. And this shows you why. Okay, so this is actually everything I want to talk about KNN. We can just wait a little bit to get the results in which it will show a 2 by 3 subplots of the things here. It will be k equal to 1, 3, 5, 10, 20. Include, here's only 1, 5, 10. So that is the thing. So in the next class, I actually have finished the slides already. Wrong again. Okay. Actually, I don't know why it is wrong. I'll already make it to be 2, 3. Here, here. Here's still 2, 2. That's the reason why. But anyway, if you're interested, you can just run a code. I don't want to waste everyone some extra 5 minutes or something. How many minutes? That's gonna be today's class, and I believe I've already uploaded lecture 7. To let everybody know that our class will finish within 2 weeks. 1, 2, 3, 4, 5. We will have 5 more classes. So what I'm planning to do is, first of all, we will finish this lecture, the homework here, and then in this one, on June 19th, we'll have, or maybe 17th, probably 19th, we'll have the second homework, and the second homework we'll do on this day. However, this day will be the last day of our class, and hence for the third part, which is the unsupervised learning, you won't have homework. Instead, you will directly have a final exam. However, don't worry, the final exam won't be like, oh, 1 hour or 2 hours, you just let everybody do. No, I will give you I haven't figured out, but at least 24 hours, at least 24 hours to finish the homework. And as long as you make it a practice after the class, I would say the problems should be easy enough. And in previous years, the results are all pretty good. So, okay, here we go. Finally, I got this. Okay, here we go. I should make it a 3 by 2 instead of a 2 by 3, actually. However, you can see that with the increase in this specific example, actually, the predictions are better and better. You can see, especially the buildings and the greens, the greenery, you can see the results are very, very good. Even for the parking lots versus the streets, you can see here, the results are actually better, improved. Okay, so that's everything about today's class. Thank you very much and have a good night. Bye bye.